Because we're going to work with two different locations for files, and sometimes we do work directly with the terminal, although I like to use tools, I'm going to just take a minute and give you some tips in case you're new to Linux like I was when I first started with Hadoop. And so we'll start here. So these are your Linux shell commands, your terminal commands, and I'm actually going to show you a couple of them in just a couple minutes. So the first tip I'm going to give you is when you're using the terminal, you want to use your tab key because it's going to complete paths and commands for you. And here's some common file system commands. ls is going to list the contents of the current directory, the names of the files and folders. cat is going to read or display the contents of a file. So if you had a text file, it would read the contents out to the screen. makedir is going to make a directory. cd is going to change a directory. Sudo, and then a command, means run as administrator or super user. chmod, some file, shows or changes permissions. There are a lot more, but these are the ones I commonly use in Linux. In addition to the Linux file system, we're probably going to use HDFS with Hadoop. So notice all these terminal commands start with the word Hadoop, and then fs for the Hadoop file system, and then they're very similar. So for example, the first one, Hadoop fs-cat file, /, file, is going to read the contents of that file from the local file system. The next one you see is make a directory, but this is make a directory not on the local file system, but on the Hadoop file system. And then copy from local, that would be local file system, put local file into the Hadoop location, and then here the next one I've shown a sudo command, so run as administrator, running a jar or a Java file, and then I have an ls for a Hadoop directory, a cat reading the contents of a file from a Hadoop directory, file 1, and then a git. So the tips are, of course, sudo, which you find yourself using very frequently, and then some Hadoop configurations use Hadoop DFS rather than FS, so you just need to check your vendor documentation. Now I'm going to show you in the Cloudera virtual machine a little bit of how this works. In the Cloudera virtual machine, we can use the terminal to browse the Linux file system. So we can type in pwd for present working directory, and that shows where the directory prompt is set. I can type in ls, and that's going to list the items inside of that directory. And again, just to kind of give us a visual on this, I can double click on this Cloudera home, and you can see that I have datasets and datasets. So this is what we're used to in terms of working with the file system. Now what's going to be new for us is this abstraction layer that's sitting on top of this, which is the HDFS file system. So if I type in Hadoop file system -ls, I'm going to get something completely different. So first of all, I see the permissions, and now I see different objects. And you might be wondering, well, this seems very confusing. Is there some kind of browser or something for this? And Cloudera does provide that. So I'm going to go ahead and go over to Hue and kind of show you how that works. So inside of Hue, I've got a file browser. Now this browser, as you see, is for HDFS. So if I click on it, so I'm currently at the position of user Cloudera. So if I want to work at the level of user in HDFS, I click user, and then you can see I've got these directories here. So if I want to make a new directory, I could use the makedir command, or I'm going to be really lazy and just say directory, and I'm going to say training. And so now here it is in the list. So now if I wanted to put something inside of this, I would go to this directory, just like we do on the file system. That's why I really like this browser. I mean, again, you could do this from the command line, but I think it's just easier this way, especially when you're dealing with two file systems. Notice you can upload a file, or you can upload a compressed file. So I'm going to upload a file that I specifically downloaded in preparation for working with this. So first I have to get the file. So the file is actually in downloads, and it's the text of Romeo and Juliet, Shakespeare.raw, kind of a weird file format. I'm going to go ahead and say open, and there it is. So now if I click on it, I can actually view it inside of here. Now if I wanted to do this same thing inside of the terminal, then what I would do is the following. I would first do an ls going to the level of the new directory to make sure the file is there. And there it is. And I'm going to just close this because we don't need this right now. And then I'm going to read the file. Do you remember the command for that? You have to put the extension. It's not ls, but cat. Now this is a long file, so I'm going to use the convention tail n50 so I don't see the whole file. And this is the end of Romeo and Juliet. Now you might be wondering, why do I want this file? Well, as we prepare for word count, this looks like a great candidate for us to run our mapreduce word count. It's a bunch of words in a text. very common example to start with. Now going back to hue, you can see we're inside of here, and I just prefer working with it. But again, I'm showing my bias for the Cloudera distribution. All the major distributions have some sort of browser. But again, the reason I wanted to take the time to show you how to work in the terminal is because so many of the other Hadoop exercises and samples that I see don't use a browser at all. But you can, use whichever one is convenient for you. So going back to where this was again, it's right over here under File Browser, and you're working with the HDFS file browser. Use job. It's easier to do it in Hue than from the terminal, so we're going to start there. And I'm in the samples at the home page in Hue, and you can see that there are some jobs here. Here's a mapreduce that sleeps. So I'm going to go ahead and open this up. Now it opens in a complex environment called Uzi that I'm going to cover in a subsequent movie. But inside of here, I've got a sleep mapreduce job. It just basically runs a word count and then it sleeps. Now these samples are read-only, so what I need to do is make a copy of this, which I'm going to do by clicking copy, and I'll call it copy. And then I'm going to go into the mapreduce job here and click edit, and I'm going to call it demo. Now if I wanted to, I could just run it from here. And notice the compiled code is under this location, Hadoop examples jar, and I could just run it from here. And here I've got my parameters, which are, I've got one reduce task, I've got a mapper class, a reducer, the map out key, the map output value, and some other parameters in here. I can also add properties, and I can look at the advanced. Now I can schedule this, so the execution environment here is pretty fancy. And I wanted to show you this because as developers, when you write your MapReduce jobs, you're writing them in Eclipse, and you're usually using unit tests to test them. But in production, they're usually run in this kind of an environment. And I'm going to go ahead and click Done. And then I could schedule this, but just to show you what it looks like, I'm going to submit it. And I need to save it. It warns me there was unsaved changes. And I'm going to put a really, really small sleep time in here. This is a demonstration of a job with the sleep time in it. And now you can see here's the job statuses. This is what I was talking about in an earlier movie, where you can see in a lot of these enterprise tools what the status of jobs are. And then you can see you've got an actual job browser too. So there it's sleeping. Another thing that's important is you have an ID. All executing jobs have an ID because they're unique, and that's what you use to track them. Notice on the bottom I can kill or I can suspend this job. If I want to, I can go over here to the job browser as well, because Uzi is actually a coordinator where you can run more than one job at a time. It just happens to be where Cloudera puts their sample, because again, from an enterprise standpoint, it's really common that you're going to chain jobs. And you see this little icon over here? These are your logs and your nodes. And it's a visual cue of the execution process. Now it's a little bit faked here because how many nodes do we have in the pseudo-distributed example? We only have one. Why does it have three? Because the default for HDFS in fully distributed is 3 copies of the data nodes. You may remember that from previous movies. So I'm over here in the job browser just to give you a sense again of the kind of information that you get. And you can see here's the job ID. It's just a different view for the job that we started. And then it succeeded. And then we have some other jobs that I ran, and you can see most of them succeeded. Looks like all of them. I had some failed jobs earlier. And they tell you the duration, when it was submitted. And then if I want to go in and look at it, I can see information about the success. I can see the tasks. Notice there's 2 maps and a reduce. And this, looking for that word succeeded, my first attempt. And there I can see information about where it was run. If I had any counters associated with it, which I don't in this case. And logs for this particular task. Notice it's using standard out, a standard error, and syslog. So verbose logging, as I talked about, but I wanted to kind of give you guys the reality of this as you were looking at it. So this is at the level of the task. Now if I go back to the job, I also was showing the attempt there. So then I can go in and I skipped over this kind of quickly. There's 2 mappers and 1 reducer here. So if I go to the reducer, again, we have a succeeded. Now, where did this succeed? What succeeded? I didn't show you the paths going in, going out, so I can go back over to the file browser. And I think it's under test output, and there's the _success message. And really that's all it is. It's just _success. That's the message you're looking for. But where's the data? Part-M-00000. And you can see this one looks like a pass-through. It didn't do a word count. This is basically a different Shakespeare that I ran earlier. Now, if this were processed, then it would be a list of key values, so words, comma, count. But this one I just did a dummy job just to make sure that it worked. And you notice I set the output location here. So if you wanted to run your own job, you go to the job designer, and then you could submit a job, or notice the types of jobs here. Now, as we go throughout this course, we're going to cover some of the other ways that you can create MapReduce jobs. I mentioned Hive in the introduction. We'll be looking at pigs, scoop, some of these other things. And also I mentioned in a couple movies previous, within MapReduce itself, there's several ways to do it. MapReduce, streaming, so on and so forth. So if we're going to be working on Java, so once we are done writing our Java, how would we then submit it? We would jar it up, and then we would give it a name, and then we would point this to our jar file, and then we would run it. So it's really pretty easy. There's the jar path. We would just put that in and pass the arguments and save it. So this is an easy wrapper for you once you're done writing your jar file to run your MapReduce. Now, from a testing point, you usually will just test it inside of Eclipse, and often you can use a unit test or some kind of real simple test so you don't have to deploy it to production. Some people do that. I actually like to jar it up and then run it through a either simple Cloudera instance, which just uses a local file system, or a pseudo-distributed, which uses a single HDFS node, like the one I'm showing for this class. So I wanted to share with you the processes that I actually use when I'm working with MapReduce code. As we continue learning about MapReduce, I want to add some more context to our visualization as we get ready to start coding. So we see that we have input starting on the left side, and the first step is going to be splitting that input so that it can be chunked or processed physically onto each of the map nodes. Now there is a default method in the MapReduce API that you can use, or you can override it depending on the type and size and processing that you're going to be doing to the data. Then the mapping code will execute. You, of course, write the map method. The shuffling is done by default along with sorting, but can be overridden if business needs necessitate. Then the reducing code is executed based on your logic, and the final results are aggregated. You also write that code. So if you look at the diagram, the code that you're going to be writing for every MapReduce job is the mapping logic and the reducing logic. Optionally, you can override the default implementations of the other phases. The MapReduce ecosystem is evolving. You may remember from earlier movies that MapReduce itself is more than 10 years old. So version 1 is very commonly in use. It's been out there for a while, and it's under the top-level library org.apache.hadoop.mapred. Version 2 has been out for a few years and is slowly starting to be the standard. At this time, however, you're going to see production code in both versions. Now, some parts of the API are almost identical, and some other parts are quite different. So we're going to start with version 1. But again, this is just a tip when you're looking at sample code. If you see org.apache.hadoop.mapreduce, you're looking at version 2. So you want to be really careful to not mix your code and to really understand and research which version you want to work with in both proof of concepts and production environments. So in addition to the MapReduce API, if you're using HDFS, or really any other parts of Hadoop, you're going to have some other libraries, and I've listed the core libraries here. You can see that they all start with import, org, Apache, Hadoop, assuming Java for the import. And then we have the file system paths, the config, the IO, and the util libraries. These are really common libraries, and there are more that you might use, many more actually, but this is kind of like a baseline. Now, because I tend to write only with MapReduce 2 code, but I wanted to start this course with MapReduce 1, We are now going to review the code used to write a mapreduce job with the version 1 of the API, and we're going to break it down part by part. So we're going to start with the map class. So I want to point out a couple of things here. You can see the class is static, as I mentioned in previous movies, and it extends the mapreduce base. You'll notice that the types are familiar but different. So we have the mapper taking two text types, but two types that have the word writable, long writable and int writable. And as we delve into this, it will become clear why. Then we have private final static int writable initialized to 1, and then we have a private text word new text. This is our key and our value. You might remember for word count, you have a value of 1 for each word that we find. That's what the int writable is, and the text is the actual text of the word. So now in our map method, public void map, we have a long writable, which is the key, and a text, which is the value. Then we have an output collector, which takes the text and int writable output, and then in this case we use a reporter for status. And then we throw an exception, a file exception if we can't access a file. Then we have a string align the value to string. And then here we have an interesting utility class, string tokenizer. And we create an instance of it against the line. So what does this do? This is one of the utilities in the mapreduce API that breaks down words. Now, if the default method of breaking down lines into words is adequate for your business case, you can just use a string tokenizer. But many times in production situations, you have to extend or perhaps replace because of either performance or the logic isn't exactly what you're looking for. Maybe you have foreign characters, maybe you have some considerations that the default string tokenizer doesn't take into account. Then you have a while loop. While the tokenizer has more tokens, then take the word and set the tokenizer to the next token, and then collect in the output collector word and 1. So what this does is this runs on each one of the physical nodes, and it takes the chunks of text from the HDFS file system by default, and then breaks them into a set of key value pairs, the text of the word and the number 1. So the next part of this is the reducer code. So again, we have a public static class reduce, which extends the mapreduce base, and it implements a reducer, taking text and int writable and text and int writable. And it implements the public void reduce method, taking text key, an iterator of int writable, the values, the output collector of text and writable, the output reporter, and throwing the file exception. It creates a variable called sum with an initial value of 0, and then we have a while loop. So we look at the values and we run the hasNext method. So then we take the sum value and we plus equal, which is sum plus the values, next get, and add it to the sums. It's a collector. And then we pass that output collect, the key, new int writable, the sum. So what that means in English is we're aggregating or we're counting up the number of words of each type. To run this in mapreduce 1, you write a main method, and inside of it you create an instance of job configuration or job conf, and you pass in the wordcount.class. And then you set the job name, set the output key class, the output value class, the mapper, the combiner, the reducer, the input format, the output format, the file input format, the file output format, including the path, and then you run the job. There's this combiner class. It's called a local reducer. What it does is it performs an aggregation or adds up the keys and values on each node so that less traffic is sent across the network to the reducer. Let me make an example. Let's say you're processing some text. So you have the word the, and rather than sending the key and value, the 1, 100 times or 1,000 times from each node, if you run a combiner, you'll send the 100, the 101, the 102, so on and so forth, the count of it across the network, which can really improve performance. Now, the interesting thing about the combiner is it's not guaranteed to run. It's an optimization. So it is optional, but it's a really common pattern, and so I left it in here. So the key components of the Java implementation of MapReduce are the input and output, and I deliberately didn't go very deep into the write and write comparable at this point. I'm going to do that coming up just in a minute here. And then we have the mapper, reducer, the partitioner, the reporter, and the output collector. Those are the key components. Now it's time to talk about those writable data types. You may remember that I talked about HDFS files as being immutable. So how do we perform looped aggregations? we have special types, which are extensions beyond the base Java types, and they're required for MapReduce. So you can see them listed here. So you've got everything from a Boolean writable all the way to a long writable. And you can see that text doesn't have to be designated as a writable. All the numeric values do, though. And notice they're described as wrappers. They're wrappers for the Java primitives. Notice the last entry in the chart, your writable. For some situations, it makes the best sense from a performance standpoint for you to write a custom type. To do that, you would implement the writable interface for a value or the write comparable of t for a key. Notice you would also have to define a sort policy for your custom writable. So there's quite a bit of code to write, although there are some good samples out there. So what would be an example of that? Perhaps like a geospatial type, where you have lat long or some combination of point in space or time that doesn't aggregate or sort in a way that is natural for the primitive types. So as we're looking into the detail of MapReduce, another consideration is input types. So you can see in the table here that I've referenced some of the most common ones, from text, key value, sequence file, and endline, and just giving you a little bit more detail. And this is just based on, again, my experience in working with Hadoop in real-world situations. Text is obviously the default. So it gives you the description of it. Each line in text is a record, and the key is a long writable, the offset of the line, and the value text is the content of the line. And again, the main reason I gave you this information is so that you can determine if you can use pre-existing types or you need to provide some additional business logic or do some pre-processing on your input into Hadoop. And just to contrast text input, let's just take the next one, key value text input. Each line is a record. The first separator divides each line. The separator set by key.value.separator.in.input.line property, the default is the tab. Key is text is anything before the separator. Value is text, everything after the separator. So again, these implementation details are really, really important when you're running your MapReduce job. So you're going to need to dig in and look at not only the default input types, but you're also going to consider what is the data coming in, what kind of pre-processing, if any, do you want to or need to do, and how might you need to override or use different kinds of types than the defaults if you're unable to or just doesn't fit your business scenario to make any changes to your incoming data so it matches one of these input types. As with input types, I wanted to talk a little bit about output types. So I put some of the most common ones here. So you have the text output format, which is key value, the sequence file output format, or the null output format. So the text writes each record as a line of text. Keys and values are written as strings and separated by a tab, which can be changed in the mapred.text output format separator property. The sequence file output format writes the key value pairs in sequence file format. It works in conjunction with the sequence file input format. So if you change one, you change the other. Now the null output might seem really, really strange. You might be surprised to see the null output format, but there are business conditions that warrant that. So now that we've run our first few MapReduce jobs, let's talk about the different ways that you can run MapReduce jobs. In production, you're going to configure your job comp options. You're going to set things like timeout values and paths for the output, paths for the input for the data. For us as developers, we won't often use those complexities. Rather, we'll work from our IDE or our coding environment, and we'll usually either just create a jar file in our coding environment and then run it from a command line, or we could actually use unit testing framework and just stay within our coding environment. But I did want to show how a MapReduce job is actually run in production, because I think it's important to understand the destination when you're writing that code. Now, I usually run my MapReduce jobs in a GUI utility rather than from the terminal, because it's just a little simpler and has richer output. So I showed Cloudera Hue. If you use a different distribution, like for example Microsoft Azure HD Insight, there's a rich console you can use. Most of the commercial vendors have a lot of instrumentation and monitoring around job execution, because that's a core part of actually running Hadoop in a production environment. Just as a reminder, from the command line, you would issue the Hadoop jar command, and then you put the file name for the jar and the input and the output locations. Now, in terms of job execution optimization, a common paradigm is called speculative execution. And what that will do will kill long-running jobs based on configurable parameters that you set, either in the source code or more commonly in the execution environment. In, for example, Cloudera Hue, you can specify the overhead it takes to run a job, the number of mappers, the number of reducers, so on and so forth, so that a job can be automatically killed if those values are exceeded. This is a common situation in production code, so I wanted to include it here. Now, we're going to come back to the world of being developers, and we're going to dig into methods to write MapReduce jobs. We saw an example of the Java code for the MapReduce 1 API, and we're actually going to write from scratch a MapReduce job using the more common MapReduce 2 code coming up here shortly. The standard way to write a MapReduce job is in Java, and I usually use Eclipse, although you could use something like Vim if you wanted to. Some people prefer to write MapReduce jobs using the streaming paradigm, where they start with a Java scaffolding, and then they use the standard in, standard out methodology, which is like a piping, and then they can write the logic of their mapper or their reducer in their language of choice. And I see things like Python or C# or even JavaScript. Pipes is another method to write a MapReduce job, and the most common language that's used with that is C++. Now, in addition to traditional programming languages, there are a whole wealth of abstraction libraries that I'll be covering in this course that a lot of people prefer to use because they're more fluent in these particular languages. There are things like Hive, which uses a ANSI SQL-like syntax that allows you to write in a database query-like language, and then it will generate the lower-level MapReduce. Pig, which is a batch language that's used in extract, transform, and load processes where you're actually doing data cleansing. It's really common that people will prefer to work in a higher-level language. But I do think it is important that you understand at least something about the internals of MapReduce because these languages do generate MapReduce jobs. In fact, this just gives you an idea of the wealth of languages and libraries I see around the Hadoop ecosystem. So one of the tips that I would give you is you want to figure out at what level of abstraction you and your team is comfortable working with the MapReduce paradigm. If you have a group of OOP programmers at your disposal, then you may want to work with Java. Even if they're C# programmers, it's pretty easy translation. If, on the other hand, you're surrounded by mostly business analysts and you really don't have too many programmers on staff, you might want to focus on higher-level languages like Hive or Pig or some of the other ones. This is a really important architectural consideration when you're implementing Hadoop in a production situation, because you really have to have the appropriate level of understanding of the language so that you can implement the data processing paradigm in a way that's going to allow you to get value out of all that data you're storing in HDFS.